So my name is Nav. I'm a software engineer on Google's Safe Browsing team. Today I'm going to talk to you about a system that we built to protect users from malicious Chrome extensions. So browsers mediate access to everything we do online, right? From our social networking or banking or email, everything you do on a desktop computer is pretty much done through your browser, right? And in some cases, browsers have become the operating system in the case of like Chrome OS, for example. So in a lot of ways, browsers are now analogous to the operating system. So if browsers are like the OS, then extensions can be thought of as applications for that OS. They extend the default behavior of the browser, and you can build app-like things, right? You can build tab managers, password managers. You can change the look, feel, and behavior of websites. And the Chrome Web Store is the home for Chrome extensions. Although when it was originally conceived, it was meant to be an optional ecosystem, meaning there were supposed to be competing markets, and you could install extensions from outside of the store. Rampant abuse from outside the store caused a policy change in Chrome in 2014. So now it is much more difficult for you to install an extension from outside the Chrome Web Store on Windows. The Chrome Web Store is a central place for extensions, so before an extension is made available to users, extensions are scanned and subject to review. And this approach is very similar to other markets. It's not unique to the Chrome Web Store, so the Play Store and the Apple Store have a similar approach. I remember when the Chrome extensions team first talked to us about the API model and the security model. They talked in terms of sandboxes and permissions, right? If an extension asked for these permissions, it was impossible for it to access APIs that were outside of its scope, or access files on disk, or run arbitrary code in the renderer process. But our team thought it would be very easy still to write something that plays within all the rules and still do bad behavior. With a one-liner, you could do something like leak the cookie of a page somewhere else, without breaking any of the rules. So we challenged ourselves to build a system in anticipation of seeing bad behavior in this ecosystem that would help protect users from these threats. We call the system WebEval. The purpose of WebEval is to protect Chrome users, and it blocks malicious extensions from being published in the first place. And in the case that we miss something, it has the ability to disable malicious extensions from all Chrome users. This provides a homogeneous enforcement environment for Chrome users. So today I'm going to talk about our 3-year experience working with this system. I'm going to talk about the design decisions and the architecture that went into building WebEval. I'm going to talk about the different kind of malware motives that we saw, the kind of threats that we actually see, and what happens when we make a mistake. What is the cost of failure? We want to highlight that to make a real production system like ours, we have to blend human expertise and automation to keep pace with threats. So let's start with the system architecture. So at a high level, the purpose of WebEval is to scan every extension that is submitted or updated with the purpose of finding bad behavior. Here are the design constraints. One of the most important ones is to minimize malware installations. It seems pretty obvious, and that's something that our team tracks very closely over time. Ideally, zero users are infected by malware. Another important constraint is time. We had to negotiate an SLA with the web store. We had to find a balance between allowing developers to update extensions and push them out to users in a timely manner, while still allowing us time for our automated systems to find and analyze bad behavior. We also knew from the onset that humans were going to be involved in our system. That's because with extensions, even if you can trigger the behavior, if you can understand that this extension is reading a password and sending it over the network, it's very difficult to tell if that behavior is bad without understanding the context. Is this a password manager that is designed to store your passwords on the network and the user understood that was going to happen? In that case, it's not a malicious extension. But if this thing was meant to change the color of your Facebook background and it was also stealing your passwords to take you over the network, that would be considered malicious. So we knew that we were going to have humans involved, so we wanted to keep that in mind when building our system. Here's the system flow diagram here, and it may seem complicated because there's many boxes and arrows, but it looks probably just like any other evaluation system out there. First, we have a scheduler, which essentially takes all the Chrome extensions that are submitted to the store and submits them through our pipeline for analysis. Then we have an evaluation stage, which is a combination of static and dynamic analysis, but really it involves mainly installing an extension in an instrumented VM and recording everything that happens and trying to elicit behavior from that extension. Once the evaluation is done, we annotate that evaluation with data we get from antivirus engines and our own safe browsing data. For example, does the extension contact known malware phishing sites? This annotated evaluation data is then fed to our classifiers for scoring. At that point, we try to make a verdict, or our system tries to make a verdict, on whether or not this extension needs review by a human or it should be allowed to be published in the store. So we're going to dive a little bit deeper into each of these in the next few slides. So our static analysis is pretty rudimentary. We basically extract all the permissions that the extension uses, as well as where the content scripts run. We also try to measure script entropy or code obfuscation. But for dynamic analysis, it's a little bit more interesting. We try to install the extension in a VM, record everything that happens, all the network requests, and the Chrome API calls, like the extension API calls, and the JavaScript events. And I say we run a modified version of Chrome, which just has additional logging for each of these. For example, in JavaScript, we have all the intermediate strings that are being passed along so that it helps facilitate human review later, that a human reviewer can actually see the string that was passed to eval, for example. One of the main components of our dynamic analysis is what we call behavioral suites. What's important to keep in mind about extensions is that they're not applications on their own. They require, you need to evaluate an extension in the context of a website to really understand what it does. So we built these tools that allow us to create behavioral suites very quickly. We can do things like type into a login field or click a button or perform a search. And we can create these suites such that we record all the content that's happening, that's being fed back to us from Google Search or Facebook, for example, and replay these actions and the content that we received for every single extension in the store. And the idea there is we have like deterministic results, and we can compare them across evaluations. So we have things like logging into Facebook, doing a Google search, doing an Amazon search query. But we also have honey pages, which are not really don't really represent any particular page, but are meant to elicit behavior by being kind of like a kitchen sink of all the things you'd imagine in a page, right? So we have password fields, anchors, we have different iframes of different sizes and divs. Now we understand there's a coverage problem here. For us to see the behavior, we need to elicit the behavior. We need to visit a page or show the extension something that it's going to interact with. But if the extension does something on a page, like the deep page of a banking site that we never visit, we're not going to see that behavior. In that case, we need to rely on other signals that our system produces. So some of the data that we use to annotate the evaluation, and the benefit of being in a web store market type environment is we get this additional metadata that's not normally available, right? Normally you just have the extension and the manifest and the permissions it's used. But here we have some information about like the developers. So we know where they were logged into when they uploaded the extension. We also know the email accounts that they're being used and how old those accounts are. From the web store, we have the number of installations that they have, as well as the rating. So for example, in the installations and rating situation, our intuition told us that if an extension received a large number of installs in a very short period of time, but had a low rating, it was probably suspicious. Maybe users were being tricked into installing it. And finally, in scoring, we have two classifiers. We have an automated classifier and a heuristic-based classifier. The automated classifier is built on top of a logistic regression model, which is trained on a daily basis. It's trained on all prior data in our system. And there's 20 million unique features. And that may sound like a lot, but you have to remember that each IP address and domain name is considered a unique feature, so we have a large feature set because of that. The heuristic classifier is essentially a set of manual rules that are crafted by the engineering team as well as the expert reviewers. The idea here is to cover gaps until the logistic regression or the automated classifier is picked up and learned about new and emerging threats. Finally, the results of the classifiers are fed into a manual review team, which is a team of expert reviewers. And that's when a final decision is made on whether or not the extension should be allowed to flow through to the store or taken down if it's already on the store. Or in a rare case, flag the item as a false positive, meaning our system made a mistake and this is actually a good item. In those cases, we try to feed this data back into our team so we can understand where we're making mistakes and reduce false positives over time. So how well is the system doing, or how well did it do? So in a 3-year period, our system analyzed around 100,000 unique extensions. Of those, around 10% were considered suspicious by our system, and the majority of those were found to be truly malicious. This graph shows system accuracy over time. The blue line is recall, the red line is precision. You can see that we consistently favor recall over precision. And the reason for that is if you think back to the design goals I mentioned early on, is that we want to minimize the number of users being impacted by malware. And to do that, we need to catch all the malware. Because we have this human review team, we're allowed to sacrifice some precision because they can make up for it by catching mistakes in our flaggings. So we have a high recall of around 96% on average, and precision is around 80%, which is still pretty reasonable. If we wanted to have an even higher recall, we could sacrifice precision further by increasing the size of the review team. So some of the interesting features that we've picked up along the way, some of them are related to behavior. So for example, extensions that modify security-related headers, like such as CSP, or extensions that remove other extensions, though these features or these behaviors are strongly related to malicious extensions. So they have a very high precision, meaning if we see this behavior, this extension is most likely malware. On the other hand, they have low recall, meaning we don't see this behavior very often in malicious extensions. So on the other hand, XHRs, or script injections, where extensions are dynamically injecting script into the pages they visit, have a very high recall. Many malicious extensions perform this behavior. But they have a low precision, meaning many benign extensions do this as well. So these categories of behaviors alone, neither of these categories alone are good enough to build the kind of system that we have that has a high recall and a decent precision. Instead, the automated classifier is able to pick up a combination of rules and put them together to produce something that has decent, relatively good recall and decent enough precision. So for example, something that that classifier has picked up recently is a combination of the geo of the user, of the developer. That means like where the developer was logged into when they uploaded the extension, combined with the behavior of tracking images. So extensions sometimes will inject small pixels into every page you visit to get analytics, as well as calling the tabs execute script API. So these combined together, something the automated classifier was able to pick up, but humans were not, are a strong indicator of badness and help us catch a lot of bad things. Now, counter to our intuition, permissions are not a strong indicator of badness. That's because permissions are broad and coarse, and many developers are actually encouraged to be broad in selecting permissions when they first upload an extension to the store. That's because when they change their permissions later, so consider if they actually selected the permissions that they needed, so a small set, and they later decided they needed more, every single user that has that extension is reprompted again to keep the extension. And there's apparently a large drop-off. So they're incentivized to ask for more permissions than they need at the beginning. So because of that, permissions alone are not a strong indicator at all. We mentioned a few times that humans play an important part of our system. They help improve our coverage, and they help against things that are changing over time. So if we look at humans and automation together, we have a very high recall of around 96%. If we took out humans from our picture and we just relied on our automated systems, we still have a pretty high recall, but lower at 91%. It takes reviewers slightly less than 3 minutes to review each extension that our system flags. And that's because we invest a lot of time in building improvements in our review tools to help them look at the features that they need, look at screenshots, and make quick decisions. So they don't need to install an extension or look at the code. They can look at the results that our system makes. As far as latency, that was another design constraint we had, right? We had 60 minutes in which we needed to make a decision. And our median detection time is 25 minutes. And the majority of that time is spent just queuing. An extension is just waiting there for a long time, or for the majority of that time, for a virtual machine to be ready to pick it up. But this is well below our SLA of 60, so we're not concerned. And if we were, we could fix this by scaling horizontally and just adding more virtual machines. Extensions can update, however. They can become malicious much later. So although our median detection time is 25 minutes, 70% of malicious extensions are detected within 5 days, and 90% within 90 days. This was assuming the worst case scenario that an extension was bad from day one and we just missed it until 5 or 90 days or whatever. But that's not always a reality. Often what we see is an extension is benign from day one, and they're working on collecting users with a real feature that they actually provide that users really want. And one day in the future, they decide to add some behavior that is considered malicious by our systems, or ownership transfer occurs, meaning if you have enough users, you might be a target for someone to reach out to you and say, hey, we'll buy your extension off of you. And in that point, they'll add some behavior to make some money, which is often caught by our system. This graph shows two different actions over time. The two actions we take are blocking an extension. So in that case, the extension is never available to users. They never reach the public. On the other hand, the other action we take is taking down an extension that's already live. In that case, the behavior could have changed from good to bad, like I just mentioned earlier, or it could have been bad the entire time. We can see that over time, we're favoring a more proactive approach than reactive. Our system's getting better at blocking extensions than it is at discovering them after the fact. On the other hand, there's in absolute numbers, there's a lot more extensions coming through. So we think that one possibility is that developers are just constantly knocking at our door, trying to twiddle their extensions until they get through, and using our system as an oracle. So what did we learn by building the system? Well, our intuition told us at the beginning that we were going to see malware that was similar to the kind of malware we'd see in Windows binaries. That kind of malware would be like stealing your passwords or banking theft. But what we've seen over these 3 years is really two main classes of malicious behavior. One is social networking spam, or what we call Facebook malware, and the other one is ad injection. So Facebook malware, usually there's like a hook involved. There's a promise of like some enticing video, often pornography, and you might have seen this on your own walls, where people are like, hey, check out this crazy Justin Bieber video. And you click on the link, and then there's this page that looks like the YouTube player or some other video player, and it says you need a codec to play the video. Really, that codec is a Chrome extension. And what the worst part is, you don't get to see the video after you install the extension. So you're burned twice. Once the extension is installed, it helps propagate itself by writing on all your friends' walls a very similar message, right? But the real payload is that it usually contacts another server to find out which pages it should like on your behalf. And then it'll like those pages and increase their like counts. So this whole like economy around this that our team hasn't really dived into much further, but we work closely with the Facebook security team in trying to curb this sort of abuse. It's interesting because they have a different angle on it, right? We have this lab-like environment where we see what happens in a very closed system. On the other hand, they get to see what happens on their system. So it's a lot harder to cloak against them. The other main category of malware we see is ad injection. Now, ad injection is not actually prohibited by Chrome Web Store policy. You're allowed to write ad injectors, and users are allowed to have them, as long as they understand that's what they're getting and that's what they want, and that is the primary purpose of these extensions. But the ones we see don't fall into that category. Often, it's an extension that provides you with some kind of value that you actually want, and later changes into injecting ads. Some of the other interesting kind of threats we've seen, but at very few, or they're dwarfed by the kind of Facebook malware and ad injection we see, but they're still interesting to talk about. One is the manipulation of Bitcoin wallets, moving money around from the user's wallet into yours. Another one is changing Amazon affiliate codes. So when you're buying a book or some product on Amazon by reading someone else's blog, usually they would get the commission based on that purchase, but these extensions, by changing that affiliate code, will get the money instead. And it's really transparent to users, and maybe users don't even care where that money goes, but it's still a problem. Another interesting one is this Brazilian banking scam. They have this type of way they transfer money in Brazil that's very common. I think it's called Brazilian boletos. And the way it works is you print this piece of paper out on your computer that has like a barcode type thing at the bottom. And with this barcode, you can use it to pay bills. You go up to an ATM and it will transfer funds into the banking, or your internet account or whatever. But extensions, or any software that's installed on a user's machine that's malicious, it has the ability to change these barcodes in such a way that the destination account is changed. And there's nothing else on the piece of paper that you print out that a human can actually understand where this money is going. What's even worse is when you go to the ATM and scan the thing, it just says, like, thank you, your money's been transferred. There's no verification of where that money actually went. So what happens when our system makes mistakes? It does make mistakes. We catch 96% of everything, but there's a few things that get through. And what we want to emphasize here is that with fewer than 100 extensions account for over 50 million users being impacted by malware. So these things propagate very quickly, mainly through like the propagation of like Facebook malware, for example, and they can impact a large number of users. What's great, or on the other hand, what's kind of good about this system is that remediation is a lot better, a lot cleaner. We have the ability to remotely disable extensions on all users' machines, and there's much less chance of like some sort of side effect software running on a user's machine than there is with Windows binaries, for example. So some of the things that we'd like to explore, but we haven't spent a huge amount of time exploring, are things like client-side detection. Everything we do is in a lab-like environment, but users or bad developers can cloak against that, right? They can understand they're running in a virtual machine or do the payload for certain kinds of users only or at some other time. I'm sure you guys are all aware of different kinds of cloaking techniques. But it's really hard to cloak against a user. I mean, if you're going to do bad behavior, it's going to happen on a user's machine. Some of the challenges that we run into around client-side detection are being able to do it in a privacy-preserving way and in a way that doesn't hurt the performance of the Chrome web browser, right? So you might be able to do this in an enterprise-type environment where you have a little bit more flexibility in changing, in playing with that security performance ratio, or in like a university-type environment. And then, those graphs earlier about us being proactive more than reactive now, but with the absolute numbers of extensions increasing, we feel like we're playing a game of like whack-a-mole, right? We're just knocking down bad extensions, and the bad guys just keep coming. Now, in one extreme example, you could say, well, what if we just killed Chrome extensions, right? If they just went away, then the Chrome Web Store would be completely clean of malware, right? There probably would be no Chrome Web Store, but this behavior would still exist. I mean, as we get better at curbing abuse in the Chrome Web Store, this behavior moves outside of the store and is happening by dropping Windows binaries, for example. So we think a more effective way would be less firefighting and more disruption. So maybe we could learn more about this like economy and try to disrupt that. Or in the Brazilian banking system example, maybe we could work with the banks and like have them add additional challenges in the actual ATM so people really know where the money's going from, and that would like kill this sort of abuse vector altogether. So in conclusion, we did a broad study of extensions. We did 3 years worth of analysis here. The system's still running today, protecting everyone here. We have a high detection rate and a very reasonable latency. And we argue that a live system such as ours requires human involvement, and that false negatives are costly. We showed that 50 million users were impacted with fewer than 100 malicious extensions. We want to issue like a call to arms. There's some research areas I just talked about, like client-side detection and economic disruption that would be interesting for the research community to explore. And our team is willing to give you data if you want to help further the advancement of research in browser-based malware. So please come and talk to me afterwards if you want access to a bunch of juicy data to help us fight this cause. Thank you very much. Take questions.
Hi, great work. Stefan Savage, UC San Diego. I'm curious, so I think the action here on the payload side is an ad injection, because that's where the easiest and most lucrative monetization vector is. Do you have any information about what that 25-minute average takedown time translates into versus their upfront capitalization costs, either to groom an extension or to buy it in terms of number of users? In fact, does that make it not profitable or just less profitable?
Well, the 25-minute delay was actually counts for the majority of that is extensions that never made it live. It just took 25 minutes for us to analyze it, so users never got to see it.
All right, but for the ones that are old and clearly got purchased, time between it became malicious and you stopped it, do you have a sense of the money made in ad views versus the cost to purchase an extension with end users? I bet it's commoditized at this point. The users cost a certain amount.
Right, I'm sure that users cost a certain amount. We only know anecdotal kind of stuff, but I don't know. That's a very interesting question.
Okay,
thanks.
Hello, thank you very much. Yanis from Facebook. Thanks a lot for publicizing this and making it accessible to more people. One question that I have for you is, what a website can do to actually help you with classification? What's the one thing that you would like to know about what these extensions are doing that we can help you with and provide you with so that effectively we can all benefit from a faster takedown of the malicious extensions?
Right, so you're on the Facebook security team, right?
Yes, I have quite a lot of experience actually staying awake fighting them.
Yeah, so we work very closely with the Facebook security team, like I mentioned earlier. And some of the things that your team does to help us is that you have a different view of the problem. So in our case, we're looking like we look like a lab type environment, right? So it's easy to cloak against us, like I mentioned. In your case, it's very difficult for users to cloak against you. So you guys really know when an account is being abusive. So you're able to pinpoint malicious extensions that target Facebook anyway a lot more accurately than we are, right? So we get these leads back from the Facebook security team. They send us these automated reports to say, hey, here is a candidate extension that we think is doing bad stuff to Facebook based on our server-side signals. And we use that data to help improve our system, but in a way that we don't take it as ground truth. We have to figure out where the gaps are in our system and how these guys are evading our sort of behavior, right? But if you're looking at like a more automated type of thing, or we talked about this earlier on, right? Is that extensions are very interesting because the behavior itself is not bad, right? So in the extensions, in the case of Facebook malware, these guys are just taking advantage of the fact that you're already logged into Facebook. So it looks like the user actually clicked on the like, right? It's very difficult for you to tell, did the user really want that or not? So, I'm not really sure I have a great answer for like what kind of stuff you can do to help us, right? And we did talk in the paper about annotating your DOM, for example, right? Like you could say, this thing is sensitive, it should never be touched. And that would help us in the case of ad replacement or ad injectors or people who are taking sensitive information from a page like a banking page. That kind of data would help us do verification in our browser as well as maybe some client-side detection sort of stuff. But these sort of like transactional kind of things, like I don't know how we can make sense of some of that data, right? You guys are probably much better understanding in the context of what's going on in Facebook's world that this like is like illegitimate. What you guys can do to help us, Facebook specifically, is make likes worth nothing.
We don't want to do that, right?
But you know what I mean, like make this economy not worthwhile participating in.
And this is actually something that we've worked on quite a lot over the past 2 years. So like we published a paper last year at CCS, which is looking exactly on like trying to make the like ecosystem be not as lucrative enough for the malware authors. Let me ask you another question.
Sure.
When you take an extension down, how does the takedown process work? So once you flip the switch on your side, is all Chrome instances in the world able to pick this up within a reasonable period of time?
Yeah, so when an extension is taken down after the fact, there has to be some additional criteria that needs to be met before we will sort of tell all Chrome users to disable that extension. So it really depends on the severity of the problem. So we're primarily focused on malware today, and all the numbers I talked about today were strictly about malware and malicious behavior. But we use the same system to find policy violations that are much less benign, right? So in those cases, we will not tell all Chrome users to disable this extension. Like, it's fine that they have it, although it violates policy, but we want it to be better for future users. Or hopefully we can work with that developer to fix the extension, rather, and all users will get updated. But in the case of malicious extensions, the criteria that we need there is that enough users need to be impacted by it. So if only a handful of users got it, we might not push this update to everybody. So it has to be kind of an impactful update, but that's really about it. And it happens relatively reasonably, I think, within an hour.
Cool. Thank you very much.
Thanks.
Hi, this is Giovanni Vigna from UCSB. Last year, there was a paper here at USENIX about a system called Hulk that would be used to detect malicious extensions. Did you look at some of the techniques like the honey pages that are dynamically generated? Did you incorporate it? Did you find them useful? It would be interesting to hear if there was some lesson learned that was passed.
Right. So we did reference Hulk in the paper, and I'm sorry I didn't reference it today, but acknowledgement to Hulk. Yes, we were inspired by their work in the honey pages to do that similar kind of technique in ours. I think some of the features, I can't remember exactly in Hulk, that they used to like flag extensions for review. In our world, they didn't work that well because it would flood. They were kind of along the lines of XHRs and script injections, what I talked about earlier, right? It's like, it's true that most malicious extensions do those kinds of things, but it's also true that many benign things do them too. So in our world where we have 20,000 extensions that are being scanned a day, we don't have the capacity to have the human reviewers look at all of those things, right? So the features that we're talking about in the paper are not practical enough, I think, to work in a real live production system unless you have a very, very large human review team. But the idea of honey pages does seem to work well for us, specifically for like ad injection type behavior.
Perfect. Thanks.
Cool. All right, I think that's it. Thank you. Good luck, man.